Thank you for introduction, Vega. Our project is belonging to the ELI, which is inside project of the Institute of Nuclear Physics Engineering from Bucharest. So initially the project had two phases, one related to one big laser, another one related to one gamma beam generator. So we are going to discuss about the gamma beam generator. I will present some kind of overview of radio frequency generation in our project, and I structured the presentation in its 3 chapters, let's say. I will start introducing information about our project, what it is about and how it's working, how we can manage to generate the gamma beam. Second chapter, let's say, is related to low-level RF system, which is required to control the phase, the amplitude, the power of our equipment. And finally, I will present the equipment which we need to get from iTech in order to control the low-level RF system. So mainly, our system consists in one electron beam injector, and the electron beam injector comprises one RF gun generation. Later on, this electron generated by RF gun is amplified through one linear accelerator, is continued later through one transport line, which is discharging the electron beam in one injection point. Later on, following the injection point, the electron beam will be charged in a storage ring. Later on, in this storage ring, there is an optical cavity where we have the final inverse Compton interaction between the electron beam and the high power laser, generating finally the gamma beam here. So mainly our system can deliver some variable gamma beam energy. So we can generate from 1 mega electron volt up to, we are going to do this. We still didn't accomplish the target, but we hope we'll finish within next 3 years. So we can adjust the output gamma beam energy between 1 mega electron volt to 19.5 mega electron volt. How we can adjust this? So we can adjust by changing the energy range of the electron beam between 234 to 742. And in the same time, we can change the laser power, I mean the frequency. We have 2 frequencies used for generating the photons by the laser. One is infrared, which is 1030 nanometers, and the other one is green, which is 550 nanometer. This laser cannot be changed automatically. They can be changed only manually. So in order to change the energy of the gamma beam, we have to stop the equipment and we have to change the laser between these 2 values. But in the same time, the energy of the beam can be automatically changed. So we can adjust somehow automatically some kind of level of the energy of the gamma beam. Okay, so later on I will introduce you the main components of the injector system. So the electron beam is generated by one cathode. This is a copper cathode which should be placed here. This copper cathode is hit by some laser. This laser can be controlled at one speed between 1 and 50 hertz. So, and later on, after the electron beam is generated. It is amplified by some RF high power signal, which is generated by one klystron of 7.5 megawatt, Canon made, and this klystron is powered by Scandinava modulator K100. After the RF S band 2.8 gigahertz pulse signal is generated, will follow some waveguides. Following this waveguides will arrive in one hybrid, 3 decibel hybrid, where the power pulse is splitted in two sides. One side arrives to the electron beam generator, and the other side is arriving in one standing wave, which will amplify the energy of the beam up to 13 mega electron volt. Okay, let's continue with some information about the linear accelerator. So, as I told, this linear accelerator can charge the electron beam up to a power of 800 mega electron volt. So how we charge this? We use 5 modules. Each module has 4 structures, and each structure has 2 meters length, and each meter is charged with 20 mega watt power. So finally we'll have 20 structures. These 20 structures with 20 megawatt power will arrive finally to 800 mega electron volt energy. So also in this linear accelerator, we have 2 analysis stations. We'll have some dipoles which will directionate the electron beam in order to be analyzed. Mostly we use to measure the emittance, which should be less than 5 micrometers, and also the spread energy. And beside this, we have at the end of each module a group of quadrupoles. They could be in groups of 3 or 4, and they are used mainly for focusing the beam. We can focus horizontally and vertically, but also these quadrupoles are used for steering the beam also horizontally and vertically. So we are going to continue our project probably next year with some BPM acquisition from iTech, because between the quadrupoles we have to introduce one BPM which will detect the position of the electron beam in order to adjust by follower quadrupoles. So a few words about how we charge the RF pulse energy for the gamma beam generated by the RF gun. So we use for each module one klystron of 50 megawatt power, which is powered also by the Scandinava modulator. And the pulse energy will arrive in one sled. This sled is a kind of passive amplifier, and its role is to compress the pulse generated by the klystron. Almostly, I mean, the pulse generated for the klystron has a length of 4 micrometers, and the sled is compressing the pulse in less than 1 microsecond, and will raise the power almost 3 times, comparing with the power generated by the klystron. Later on, the signal which is generated by the sled will arrive in one hybrid, the 3 decibel hybrid, which will split with a difference of 90 degrees angle the pulse. And later on, this pulse split in 2 pieces will be split again in 2 pieces in order to charge 2 by 2 all the 4 structures. So this pulse is going to be introduced in each structure. And after the pulse is introduced in the structure, in each structure, it is circulating. And later on, after it is filled, will be discharged through these RF loads and will be transformed this energy into heat, which with help of some cooled network will be maintained under control. So the working temperature of all equipment is 25 degrees Celsius. So let's go further. This is what is the shape of one accelerating structure. So we have to keep in mind that we have 56 cells, and beside the 56 cells of the accelerator structure, we have also cell for connection, and another one where is coming from the pulse, and another one for exit. So in these cells, the phase is changing with 120 degrees. And one of the reasons why we have why we need low level RF equipment is to arrange the emission of the electron beam to be synchronized in such a way that at the entrance of each module to be in the same phase. And these things could be done, as I will explain you further, with low-level RF equipment. Also, we need low-level RF equipment in order to analyze the forward and reverse pulse. And we have some couples at the input and the output of each structure, but I will give you more details later. So this is the whole module, which comprise 4 structures, as I explained, and this is the sled which I introduced you before, and the hybrid which shares the energy into half, one side and half to other side. Okay, so as I told you, this sled is having some kind of resonant cavities, is amplifying the RF pulse generated by the klystron. And we have a problem that when the sled is amplifying this pulse, is generating a very high peak. So we want to flatten this peak. So in order to flatten this peak, we need also to change the pulse phase generated by the klystron in order to diminish the peak. So here is something similar which I've seen that we wanted to do the same thing. You know, this is the peak which will be generated by the sled, and we want to flatten it, and we have to change in very short time the angle generated by the RF pulse from the klystron with 180 degrees. So we need one very fast operating low-level RF equipment in order to perform this, in order to flatten the peak of the energy, while will arrive finally 80% of average power generated by the klystron. So this is the second chapter of the presentation related of our low-level RF system requirements. So mainly we have we need 3 levels of frequency in order to operate our network. Main one is 2.8 gigahertz, and the second and third ones are 20th harmonic of 2.8 giga, and the last one is 40th harmonic. So mainly we need to use this main reference frequency to give a pulse to the injector klystron of RF gun. Later on, we have to synchronize injector laser with continuous wave reference signal for having frequency stabilization. Following, we have to send the pulses for all 5 linear accelerator modules. So in order to do this, we have to give a signal for the modulator, which will be amplified by the klystron and later on by the sled. But we have to keep in mind that we have to do this fast phase shift at the klystron signal before the sled is comprising and is raising the signal. And also we need the main frequency in order to have a reference for BPMs, which will measure the signals in order to adjust the electron beam position and focusing. For the future development, we'll have need also for the 148.2 megahertz, which will be used in the cavity amplifier, will be in the future amplify the laser, and also will use for future BPMs placed in the ring. And the last frequency will be used for continuous wave reference signal for the laser injector. And we need also to have clock signal which will be linked by the AC main frequency in order to have a more stable operation. So here I resumed a few use of the low-level RF timing and synchronization system. So we need, as I told, these trigger signals to be synchronized with AC mains with 50 Hertz frequency of the AC main. And we need to provide transistor-to-transistor logic level digital triggers with jitter to be less than 50 picoseconds in order to synchronize the low-level RF system. Okay, about the delay pulse, doesn't need to insist so much. And also, all this information are related to the phasing, energy, and amplitude of the signals which will be generated in order to control the whole equipment. As I told you before, we have some analyze of the RF pulse signal within each structure, but not only in each structure of the accelerator, but also at the input and the output of the sled. So we analyze forward and the reverse signal in order to adjust the generation of the low-level RF signal in order to be in phase and amplitude and in the power each module together with the laser which is generating RF electron beam. So totally we have in RF gun 3 directional couplers, one at the entrance of the sled, another 2, one at the entrance of electron beam generator, and the other one at the standing wave structure here. So totally we have 3 for forward, another 3 for reverse. Totally we have 6 channels to collect the signals from the RF gun. And for each module, we have totally 10 directional couplers, 2 placed at the input-output of the sled, and the other 8, yes, 2 per structure, 8 in total for module. So we'll have finally 10 directional couplers and 20 RF channels. So this is the equipment which we intend to buy from the iTech. So this is the reference master oscillator, which will deliver the main reference frequency, 2.8 gigahertz. Here we have also the frequency stability and other parameters. As I mentioned here, I marked with red are the offers, I mean the parameters of quality better than what we asked from this reference master oscillator. So this will be two pieces. Later on, the signal generated by the reference master oscillator needs to be amplified and filtered and amplified, and we use 5 distribution amplifiers for reference master oscillator. So these distribution amplifiers accomplish our requirements, and also I will show you the position where we are going to use them. So our accelerator will be placed in two rooms. First two modules will be in room EP10, which is present here. This is another second room. And in order to synchronize operation of all equipment, we needed to introduce our equipments nearby the accelerator and the RF gun. So we decided to share in 3 racks all the equipment. So here we have one distribution amplifier, placed in the room GP09, another one in GP07, and the last one in GP05. Here will be the positions of the racks, also together with another equipment. So the next type of unit which will get from the iTech is trigger signal generator. And this trigger signal generator we'll use to synchronize the RF signals. Here also we got some extra benefits from the parameters of the trigger signal generator delivered by iTech. Now this is equipment is S-band low-level RF system. This equipment will generate the signal and also will pre-locate the signal collected from these directional couplers. We'll analyze, and depending of the level of the pulse signal, will adjust the generation of the RF signal. So here we have this S-band low-level RF system shared in two type of equipments. So one is used for line-up, I mean 5 pieces for each modulator of the line-up, and another 2 components are used for the RF electron source in order to collect and generate the signal. And this is the last type of unit, clock transfer units, which we need because we take into consideration the distances are longer than 40 meters. We understood that it's better to use optical fiber equipment to transfer the reference signal. So we got these 3 pieces of equipment to transfer the reference signal over longer distances between those 3 chambers where are going to be placed the racks with the Libera equipment. So now what I want to underline at the end of my presentation is what we achieved up to now. So here we have some pictures which show that we finally succeeded to install all the utilities which will be used for operation of the line-up. So we have already installed the power, the DC power, the AC power. The cooling system is fully completed. Also, we succeeded to place the plates for the future positioning of the accelerating structures. We started to place on the position the sleds. These are images with the sleds, the RF gun, and also we started to work for placing the hybrids and the waveguide structures. Here are also we succeeded to place in the position the whole power supply units for the whole network of quadrupoles and dipoles. And here is a picture with one group of quadrupoles, unfortunately cannot be seen so well, and one dipole, and we tested them, and we measured the magnetic field, and it is work well. Now we are in the procedure to fiducialize the quadrupole magnets and the dipoles in order to have 3D positioning of the magnets in order to be fitted exactly on the middle of the electron beam. So here in these rooms we have the future positioning positions of the racks with the Libera equipments. So here will be in the first room the position of the rack. Here are the modulators. This is RF-GAN modulator, and this is first accelerator module modulator. And here is the other positioning of the second rack with Libera equipment, and here is the third one. We place them. So in this moment we are going to finish power supply and introducing, we have a small work in order to place some cable tracks to be just positioned on the top of each rack in each room. So these are the two racks with the power supplies for the magnets, which are already in the positions, and the cables are available for the magnets. So this is my presentation. I hope we'll succeed to achieve this most advantage gamma ray beam system in the world, and to finish all the project in 2026. And we hopefully at the end of this year will commission the LLRF. So thank you for assistance to my presentation.
Do we have any questions?
Maybe have a short question about the timeline. So in LLRF commission, that means already with the BIM in 2024, or?
I was expecting to be asked about this one. So theoretically, I mean, if you were asking me at the beginning of this year, I would have told you with closed eyes that we are going to commissioning. Now I'm not 100% sure, but we hope at least to be all the equipment placed in the position and to be ready for the commissioning. Probably will not commission it, but will be near to perform commissioning.
So at least installation.
Yeah. We want to be all the equipment on the position. I mean, the waveguides and the klystrons and the magnets. Okay, I mean, some of them, probably the magnets we can place in the position very soon. A little bit delay will be required for installing the klystrons and the waveguides to charge the RF pulse to the accelerator structures.
Anyone else?
The delays are, if there will be some delays, you see them because of the suppliers being a bit slow, or maybe the team is too small.
No. I would say no. I would say that is because we needed to sign some assistance contracts with some companies, and the bureaucracy is pretty big, and we still not succeeded to sign those contracts. I mean, we need some kind of fine-tuning assistance. I mean, we are going to do ourselves, let's say, the rough tasks, but for the fine-tuning, previously performing the commissioning, we need the company to just to check, you know, to brief that everything is 100% well done. So we are a little bit in delay with these companies which are going to assist us to finally commissioning the equipment.